Today we are going to see the transverse vibrations. That means that we are going to this. I'll read this. When the particle of the shaft or any object move approximately perpendicular to the axis of the shaft. So that is, when the particles move perpendicular to the axis of the vibration axis of the shaft while it's making periodic repetition, then it is called transverse vibration. That is, mostly it occurs in the beam. So here in the transverse vibration, with the principle of a transverse vibration, we are going to find out the natural frequencies of the beam by applying stiffness matrix, mass matrix, and lumped matrix. This is all the way. This is what consistent matrix. It is written here, consistent. This is lumped matrix. Both the things we can use to find out the natural frequencies. So this is the general equation. It is same for bar. It is same for beam. This is finite element equation, stiffness matrix, mass, natural frequency, displacement and the force. And this will become always 0. We are not considering any forces at all. So this is the equations. So okay. Determine the natural frequency of the vibrations of the beam fixed at both the ends, and figure the beam has mass density, that is rho, modulus of elasticity, cross section area, moment of inertia, length and simplicity. For simplicity, the longhand called beam is discretized into. So why do they longhand calculations? They say means it is enough element 1. This problem is more enough to have only one element, but for longhand calculations, for the simplicity, we are dividing into 2. It is not necessary. So length L1 is equal to N, length L2 is equal to L, and this is 2L, isn't it? So it is LL. So this is the data that is given in the problem I have written. Our aim is to find out the natural frequency of the vibrations of the beam. Now I have discretized and made all those things. Because it is a beam, we have to mention the shear force, that is shear force moments, and I have not mentioned any deflection because we are work only rotations. I am making it out. So see V1 theta 1, V2 theta 2, theta 3, V3. So this is these are the things we have mentioning here, and from this we can understand clearly that both are fixed, and these two terms become 0, these two terms become 0, only this rest. So easily we can find out the boundary conditions. So this is what is this? This is the stiffness matrix of the element 1. So for this I discretized element, and this element I am taking this element, discretized element. This is the discretized element. So this is the formula. We are going to apply this here. See here we don't want to apply any length value because L is L here. Here it is. This is also L, and this is, and here from here to here this is L, and this is also L. So we don't want to, because same thing we can keep it here, and mass stiffness matrix of the element 2. That is why easily it is done, because it is L. So this some now we have to assemble. So this, for assembling, these nodes are very important. This is nothing but V theta 1, V1 theta 1, V2 theta 2. This I have written for simplification 1 2 3 4, 1 2 3 4. So this is from here, this part, no, 1 1 1 2 3 4, this part, and 1, this is 1 2 3 4, and 3 4 5 6. That is one here. Okay, and now we are assembling this. You know how to assemble this. This is, please look into these two and then assemble 1 1 1 2, and in that way you have this 1 1. So 12. Here 1 1 is there? No. So 12. 1 2. It is 6L. Sorry, 1 2 is here? No. So this is 6L. So in that way, please 1 1 1 2 1 2 1 3 1 4. Here 1 5 1 6. In that way, because it is a 6 by 6 matrix. Here we are getting 1 2 2 2 4 6. So 6 by 6 matrix. Here the displacements are 6. So 6 by 6 matrix, or we are getting here. So according to that, please do the assembling. And now find, we are going for mass matrix. The mass matrix here, this is the lumped mass matrix I have taken. Next problem we will go for consistent mass matrix, and this is the lumped mass matrix. 1 2 3 4. So these are the readily formula. So this is rho A L. L is a L, same thing. So element 1, element 2, I got this two both I am assembling here. Easily you can make it out. And this is the assembled matrix of the beam. Now going to apply these assembled matrix, stiffness matrix and mass matrix into the global matrix of the beam element. So I got this equation completely. I have substituted the value of stiffness matrix, mass matrix and this one. So this is what I got. So now we have to apply, after getting the finite element equation, what we are going to do, we are going to apply the boundary conditions. That boundary conditions, we know both ends are fixed. So this is a 0. This becomes 0. So V1, theta 1, this one. So no displacements, no rotation. So this is the 0. So V2 is equal to V2. It means what? V2 have a displacement and V3 have it is there. So we don't want to consider this here because we are going to find out the natural frequency. We are not going to concentrate on the displacements. So this part is to solve this problem. So here we are taking up the boundary conditions and using it to solve the problem and find out the natural frequency, that is omega square. So now okay, now I am writing returns everything and I am cancelling 1, 2, 3, first row, second row and fifth row, sixth row. Columns and the rows are deleted completely. This, fifth row, this sixth row. So remaining part I have written. Remaining part, this is what I written. So this is what I am getting it. So rho AL gets cancelled. So only omega square remains. So I am getting this part. Only this part I am taking it because it is a homogeneous equation and we can take the coefficients of this V2 and set this coefficients matrix of homogeneous coefficient matrix, this one of this coefficient V2 T2 coefficient matrix, set it to 0 to find out the determinant. So this only this part I am taking and setting the determinant is equal to 0 and finding out the omega square value. This is the coefficient. These are the coefficient of this matrix. So by setting out that is why I have written to obtain a solution set of homogeneous equation, we set the determinant of coefficient matrix to 0. What is the coefficient matrix? Is V2 theta, this one. This coefficient means setting it to 0. So now we are going to omega square is equal to lambda and this is equal to mu for simplification. Lastly we'll substitute that this value in the mu and find out. So now we are getting this. Now you minus this. Now after minusing part, this you will get this in this. So now you are getting this one. Multiply inside this into this into this. I am getting this into this and this into this. You are getting this. Then take out simplification. This part and I am taking this part. So L square mu square this part. So I am taking 8 L square mu outside and I am getting this part and this part. I am getting this one. And this are remaining. So minus lambda I am taking, this part I am getting. So 8 L square minus lambda. So I factorized. I got this equation. So lambda 1, lambda 2. Lambda 1 is equal to L square mu. So lambda 1 is omega square. We have set it out, right? Omega square is equal to. So now I am getting L square mu. This L into this value, substituting all those values, taking root. So I got 2.22 L cube by EMA. In same way, we have to go to lambda is equal to 24 mu. So omega square is equal to 24 mu. So omega is equal to root of 24 mu. So this is L4 will come out L square. 24 root is 4.9. So this is omega 2. So we got the natural frequency using lumped mass matrix. Now we will see in the next problem to use the consistent matrix. Thank you.